Welcome back. My name is Dr. Elvis Asong. I am a senior climatologist at Climatology Inc., an adjunct professor in the Global Institute for Water Security in the University of Saskatchewan, and an associate of the Climate Risk Institute. Today, we will shed further light on some of the key concepts covered in the previous session on understanding observational data and considerations for their use. Here we'll take a closer look at station data, gridded meteorological data sets, reanalysis data sets, and remotely sensed and quantitative radar estimates. We will now take a closer look at some of the main observed climate data sets often required for water infrastructure climate risk assessments. We'll look at station data, gridded meteorological data sets, reanalysis data sets, remotely sensed and quantitative radar estimates. What are station data? These are data collected at a specific point, such as a synoptic weather station, a climatology station, an agricultural station, or a hydrometeorological station. These station data are irregular in space, and they often have so many issues which we will discuss in subsequent slides. And these weather stations are either surface, for example, rain gauges, or upper air, for example, satellites. A very good example of a daily global station data set is the Global Historical Climatology Network. It contains records for precipitation and temperature across the globe. Observations. So weather observations provide important information on the past and current climate using direct and indirect observation methods. Direct or in situ observation methods include weather stations as well as the Global Observing System, which relies on ships, moored and drifted buoys, and stationary platforms to collect data across sites. Indirect observation methods include things like tree rings and ice cores, depth profiles of temperature in oil drilling boreholes, corals, satellites, radar, and LiDAR. Raw observations from sensors and measurement devices such as rain gauge stations usually need pre-processing before they can be used. For example, quality checks must be implemented, data gap filling often required, and homogenization tests are often required as quality control measures. Common surface and upper air variables observed for various networks or types of stations include air temperature, precipitation, wind, solar radiation, stream flow, runoff, and evaporation. So, what are graded meteorological data sets? Now, station observations have many benefits as well as limitations. And why do we, first of all, what are graded meteorological data sets? These are data sets interpolated based on station observations, arranged on a regular grid. You can see on the figure there, they are arranged on a regular grid from local to regional and global scales. This is a regional grid for the Nile Basin, an interpolated gridded data set. The resolution of gridded data varies from as little as a few square meters in the case of suburban data sets to 200 to 300 kilometers as found in global data sets. Similarly, temporal resolution may vary from the sub-hourly to annual time scale. So why do we need gridded data sets in the first place? Why do we need to have climate variables estimated across all locations in the Nile Basin. Why is that important? Well, one of the major problems with station data is its missing values, inhomogeneity, fewer number of stations, and issues with record lengths. In data-sparse regions such as the Nile Basin, access to graded data is essential for many studies and practical applications such as for climate risk assessment. Graded data sets facilitate the spatial analysis of climate variables and the static or dynamic visualization of climate patterns and trends, as this figure illustrates. You can be able to study climate patterns and trends from, say, the east, the Nile Basin, to the west, and from south to north, and understand how the climate has changed. It's currently changing and it will change in the future. Graded data allow for estimation of weather and climate variables at locations where station data are unavailable. I guess that is the main reason why we need climate data sets. That is the primary reason, to get climate variables at points where station data are unavailable. How are station observations-based graded data produced? Now, an acknowledged frustration for practitioners is the patchiness of data over both space and time due to an uneven geographical and temporal distribution of climate observations. Over the last decade, the availability of observation-based graded climate data sets has helped address some of the practical challenges posed by the incompleteness of observed data. While some of the observed graded data sets are based purely on surface observations, others are blended data sets, including observations from both surface and satellite-based platforms. Typically, observation-based graded data sets are comprised of values interpolated from stations for which data has been adjusted and homogenized. Examples of graded data include the Climate Research Unit dataset, the CRU dataset, and the GPCC datasets. A very good example of another graded dataset is the Aphrodite dataset. So here, graded precipitation. How is this dataset produced? Typically, the task will involve collecting some daily or monthly climate data at stations and converting the data to a particular format. There is then, in task 2, some sort of quality control of the data, and they can collect data. As I said, station data can either be from rain gauges, from satellites, from buoys over the ocean, and even from airplanes. Okay, and the next step is to integrate all these data sets and use an interpolation algorithm to grade the data and produce a regular grade. Okay, and the last step typically involves regrading the data. So they can move the data, say, from a 0.05 degree analysis to a 0.5 degree analysis, and this often is done when several data sets are to be meshed into a single graded data product, such as the Aphrodite precipitation data set. Another very important graded data product are remotely sensed and quantitative radar estimates. Remotely sensed data from satellites or aircraft provide meteorological information at fine spatiotemporal resolutions and regular intervals. Presently, there are many quasi-global, high-resolution satellite data products, especially precipitation, including the Persian dataset, the CPC morphing technique called CMORPH, the Global Satellite Mapping of Precipitation, that is GSMAP, the Tropical Rainfall Measurement Mission called TRIM, Multi-Satellite Precipitation Analysis, and currently we have the Global Precipitation Measurement Mission, and this is typically known as IMesh. And here on this image, you can see the rainfall, total rainfall snapshot over most of the Nile Basin, and this shows you total rainfall between April 27 to May 14, 2018. These kind of data are short-term at the moment, so IMesh starts basically in 2014, and this kind of data sets can be used to stress test a system when doing a bottom-up climate risk assessment. And as I mentioned, the usability of data, assessment of data needs really depends on the type of impact assessment approach to the climate risk assessment. So remotely sensed data sets and quantitative radar estimates, when available, are critical for bottom-up climate risk assessments, typically looking at sensitivities of infrastructure systems. Another important graded data product are reanalysis data sets. For example, in this figure, we show here the watch day 5 data set, reanalysis data set, that is based on the CROU plus the GPCC precipitation data set. So why reanalysis? Reanalysis data provide the most complete picture currently possible of past weather and climate, and they are a blend of observations with past short-range weather forecasts rerun with modern weather forecasting models. So they are typically outputs of some kind of a physically based model. They are globally complete and consistent in time, and are sometimes referred to as maps without gaps. However, reanalysis data products have their own limitations, just like any other data set. One, observational constraints, and therefore reanalysis reliability can considerably vary depending on the location, time period, and the variable of interest, especially extreme events. Two, the changing mix of observations and biases in observations and models can introduce some sort of spurious variability and trends into reanalysis outputs. Three, diagnostic variables relating to the hydrological cycle, such as precipitation and evaporation, should be used with extreme caution. For example, if you are doing a climate risk assessment which requires evaluating climate extreme indices, then using reanalysis data to develop those climate extreme indices should be done with caution. Why? All graded data products involve some kind of interpolation, and interpolation smooths out extreme values in the resulting outputs. So reanalysis data products should be used with caution. A very good ode to the density and distribution of monitoring networks and record and length of recorded data declining over time. Reanalysis data sets have become very popular for impact and climate risk assessments. A very good reanalysis data set is the ERA interim, which incorporates satellite estimates, and you can see here the range of satellite products which are integrated within the ERA interim data set. Some hydrologic variables can benefit from the GRACE data, so the Gravity Recovery and Climate Experiment of NASA, and all of these data sets are typically integrated within reanalysis products. I will end this session with some overall guidance on how to use climate data. So the type and source of climate data will depend on the approach of the climate risk assessment and the level of detail of the risk assessment being pursued. Always understand climate data availability, quality, and applicability. So, for example, a very fine resolution image doesn't necessarily mean that that data set is the best for your application. So, do quality control on the data and check for any kind of inhomogeneities before using that data set, especially station observations. And on a project team for climate risk assessment, always bring in a qualified, experienced climate scientist to interpret source data, interpret it, visualize it before it can be applied in any kind of risk assessment. And that brings us to the end of this session. I would like to thank you for your time and attention today.